Hello everyone. Welcome to the brand new section of the course, First Steps in Supervised Learning. In this section, we will learn about different supervised learning algorithms. We will understand the classification algorithms such as KNN and logistic regression. We will get an overview of the various variants of linear regression such as lasso regression and ridge regression. Last but not least, we got acquainted with the Iris and Boston datasets. Now we move on to the first video of this section, that is, Understanding Supervised Learning. In this video, we will learn to measure model performance with scoring functions, which include scoring classifiers and regressors. We have previously established that the goal of supervised learning is always to predict the labels or target values of some data. However, depending on the nature of these labels, supervised learning can come in two distinct forms, that is, classification and regression. Supervised learning is called classification whenever we use the data to predict categories. A good example of this is when we try to predict whether an image contains a cat or a dog. Here, the labels of the data are categorical, either one or the other, but never a mixture of categories. Whenever we use the data to predict real values, that supervised learning is called regression. A good example of this is when we try to predict stock prices. OpenCV provides a pretty straightforward interface for all its statistical learning models, which includes all supervised learning models. The most notable difference is that scikit-learn sets all the required model parameters in the initialization step. Thanks to this organization of the software, setting up a machine learning model in OpenCV always follows the same logics, as you can see on the screen, which includes initialization. We call the model by name to create an empty instance of the model. Set parameters. If the model needs some parameters, we can set them via setter methods, which can be different for every model. Train the model. Every model must provide a method called train, used to fit the model to some data. Predict new labels. Every model must provide a method called predict, used to predict the labels of new data. Score the model. Every model must provide a method called calc_error, used to measure performance. This calculation might be different for every model. Measuring model performance with scoring functions. One of the most important parts of building a machine learning system is to find a way to measure the quality of the model predictions. First, we will look at scoring classifiers using accuracy, precision, and recall. In a binary classification task, where there are only two different class labels, there are a number of different ways to measure classification performance. Some common metrics are accuracy score, precision score, and recall score. For understanding these metrics in detail, you can refer to the reference material which is attached with the code bundle. So let's start by importing NumPy as NP. And to fix the seed of the random number generator, we will add this line of code. Then, by adding this line of code, we can generate 5 random labels that are either zeros or ones by picking random integers in the range of 0 and 2. yTrue command will display the output. In the literature, these two classes are sometimes also called positives, that is, all data points with class label 1, and negatives, all other data points. Let's assume we have a classifier that tries to predict the class labels mentioned earlier. For the sake of argument, let's say the classifier is not very smart and always predicts label 1. We can mock this behavior by hard-coding the prediction labels with this line of code. This is the list of array displaying prediction label as 1. A naive implementation of an accuracy metric might sum up all occurrences where the predicted class label matched the true class label. For that, we will add and execute this code. A smarter and more convenient implementation is provided by scikit-learn's metrics module. First, let's import metrics package from sklearn. However, in order to understand precision and recall, we need a general understanding of type 1 and type 2 errors. Let's recall that data points with class label 1 are often called positives, and data points with class label 0 or -1 are often called negatives. Then classifying a specific data point can have one of 4 possible outcomes, as illustrated with the confusion matrix. Let's break this down. If a data point was truly a positive, and we predicted a positive, we got it all right. In this case, the outcome is called a true positive. If we thought the data point was a positive, but it was really a negative, we falsely predicted a positive, hence the term false positive. Analogously, if we thought the data point was negative, but it was really a positive, we falsely predicted a negative, that is, false negative. Finally, if we predicted a negative and the data point was truly a negative, we found a true negative. In statistical hypothesis testing, false positives are also known as type 1 errors, and false negatives are also known as type 2 errors. Let's quickly calculate these four metrics on our mock-up data. The output proves that it is a true positive as the achieved and predicted value is 1. Enter these lines of code where we have a true positive, where the true label is a 1, and we also predicted a 1. Similarly, we will enter another code where we predicted a 1 but the ground truth was really a 0. So, the generated output is false positive. I'm sure by now you've got the hang of it, but do we even have to do math in order to know about predicted negatives? Our not-so-smart classifier never predicted 0, so ypred equal to 0 should never be true. Here we will re-enter the previous code with a few modifications, replacing positive with negative and the value of pred and true. As you can see, the output is 0. We will again experiment with the same code with a few changes. On executing it, we will get an output as 0 again. To make sure we did everything right, let's calculate accuracy one more time with this line of code. Basically, the accuracy should be the number of true positives plus the number of true negatives divided by the total number of data points. Print the output with accuracy command. Success! Precision is then given as the number of true positives divided by the number of all true predictions. We will execute with this line of code. Turns out that precision isn't better than accuracy in our case. Let's check our math with scikit-learn by entering this line of code. Finally, recall is given as the fraction of all positives that we correctly classified as positives. After adding the recall command, print its output. We will again check it with scikit-learn. Perfect recall! But, going back to our mock-up data, it should be clear that this excellent recall score was mere luck. Since there was only a single 1 in our mock-up dataset, and we happened to correctly classify it, we got a perfect recall score. Does that mean our classifier is perfect? Not really, but we have found 3 useful metrics that seem to measure complementary aspects of our classification performance. Next is scoring regressors using mean squared error, explained variance, and R-squared. When it comes to regression models, our metrics, as shown earlier, don't work anymore. After all, we are now predicting continuous output values, not distinct classification labels. Fortunately, scikit-learn provides some other useful scoring functions. Mean squared error is the most commonly used error metric for regression problems, and it is to measure the squared error between the predicted and the true target value for every data point in the training set, averaged across all the data points. Then there is explained variance score. A more sophisticated metric is to measure to what degree a model can explain the variation or dispersion of the test data. Often, the amount of explained variance is measured using the correlation coefficient. Another function is R-squared score. It is closely related to the explained variance score, but uses an unbiased variance estimation. It is also known as the coefficient of determination. Let's create another mock-up dataset. Say we are observing data that looks like a sine as a function of x values. We start by generating 100 equally spaced x values between 0 and 10. However, real data is always noisy. To honour this fact, we want the target values y_true to be noisy too. We do this by adding noise to the sine function. Here, in this code, we use NumPy's rand function to add noise in the range 0, 1, but then center the noise around 0 by subtracting 0.5. Hence, we effectively jitter every data point either up or down by a maximum of 0.5. Now, assume our model was smart enough to figure out the sin x relationship. Hence, the predicted y values are given in this line of code. Further, we will use matplotlib to visualize the data. First, we include this code snippet to import matplotlib pyplot as plt. This line will set the style as ggplot. Then we will add this block of code to produce the plot. This is the generated line plot which displays predicted y values and ground truth data. The most straightforward metric to determine how good our model predictions are is the mean squared error. For each data point, we look at the difference between the predicted and the actual y value and then square it. We then compute the average of this squared error over all the data points. This line of code will calculate the value and MSE command will display the output. For our convenience, scikit-learn provides its own implementation of the mean squared error, so we will achieve it with this code. Another common metric is to measure the scatter or variation in the data. If every data point was equal to the mean of all the data points, we would have no scatter or variation in the data, and we could predict all future data points with a single data value. This would be the world's most boring machine learning problem. Instead, we find that the data points often follow some unknown hidden relationship that we would like to uncover. In the previous example, this would be the y equals to sin x relationship, which causes the data to be scattered. We can measure how much of that scatter in the data, or variance, we can explain. We do this by calculating the variance that still exists between the predicted and the actual labels. This is all the variance our predictions could not explain. If we normalize this value by the total variance in the data, we get what is known as the fraction of variance unexplained. Let's execute it with fvu command and observe the expected output. Because this metric is a fraction, its values must lie between 0 and 1. We can subtract this fraction from 1 to get the fraction of variance explained. As you can see, this is the subtracted value. Let's verify our math with scikit-learn. On executing this line of code, we can verify that we have achieved the same value. Spot on! Finally, we can calculate what is known as the coefficient of determination, or r squared. R squared is closely related to the fraction of variance explained, and compares the mean squared error calculated earlier to the actual variance in the data. We can do that with this line of code. The same value can be obtained with scikit-learn. On executing, we get the similar value. Great! The better our predictions fit the data, in comparison to taking the simple average, the closer the value of the r-squared score will be to 1. The r-squared score can take on negative values, as model predictions can be arbitrarily worse than 1. A constant model that always predicts the expected value of y, independent of the input x, would get an r-squared score of 0. To obtain the score, we will enter this line of code. The output obtains score value as 0. In this video, we covered scoring classifiers using accuracy, precision, and recall, and scoring regressors using mean squared error, explained variance, and r squared.